I'm now going to go through the Excel sheets with the examples that were from the lectures in the first week. We did a little bit of these in the class on Friday, but I'm going to go through the complete set here, so you have them all in one go. Right, the first example was to calculate Q, discharge, for uniform flow given a normal depth. So normal depth, remember, is the depth in uniform flow. Now this is an example using the Chesi equation. That's the equation of this form. Flow is equal to AC, C is the Chesi C, hydraulic mean radius to the half, the slope of the channel to the half. Okay, right. We were given these values all in yellow. And just remember the convention that I'm going to use. All cells that are in yellow, the values have been given in the question. And cells that are in this pinky colours are intermediate calculations, and cells that are green are solutions. I'll always try to do on these sheets as well, put in the formulae that you're going to type in, because Excel is a bit complicated, easy to enter numbers in, easy to get it wrong. So I'll put the formulas so that we can recall them easily, and we'll try and do calculations where we can check other parts of the calculation. So the first calculation is to calculate the slope, and I've done this here already. It's a 1 in 1,000, so 1 divided by 1,000. Okay, we need to calculate the area. Well, the area is just the bed width times the depth for a rectangular channel, so it's equal to V6 times by the depth, and the depth we've been given is Y. The normal depth, I've labelled it YN there. 24 meters squared. The wetted perimeter is the width plus 2 times the depth, 14 meters. Hydraulic mean radius, hydraulic radius is equal to, always equal to the area divided by the wetted perimeter, 1.74, and Q is just this formula here for what we refer to as the Chesi equation, is equal to the area times the C, which is 50, times R raised to the half, times by S0 again raised to the half. We'll get 49.68 meters cubed per second. So this rectangular channel will carry 49.68 meters cubed per second when it's flowing in uniform flow. Let's have a look at that formula again. We don't need to use those raising to the half. We can use a square root function. So let me just do this one again to show it's the same. So A times C times, we're going to use the square root of R times the square root SQRT in Excel of S0. And we've got the same number there. Okay, really simple calculation, explicit formulae. We're going to then use the, let's do the second example. It's a Chesi equation on a rectangular channel, and we're going to calculate the normal depth, Y, that's the depth, when we've been given a flow which we're told is uniform flow. So this time the flow is 30, the bed width is 6, Chesi C is 50, and it's a 1 in 1,000. Again, I've calculated here, no, it's not 1 in 1,000. I probably should have put a 1 in 1,000. Okay. Now, because we need to calculate the depth that satisfy this equation, well, we could expand the equation with the R as A over B. include the other A, but that's more complicated. We could see it's a rectangular channel, so we could put in the formulas for the A and P in here and calculate, try and calculate this YN. But it's simpler to do an iteration setting the function to 0. So the function being taking the Q or the right hand side over to the left hand side and setting it equal to 0. Just written it the other way around here. And solving for the value of y, which gives you a function of 0. Now, for this example, I'm just going to show how I've done that with the function. So looking at this function here, let's move that into the middle of the screen. I've plotted that function, sorry, this function against some guessed values of y. So I've started at 0.1 and gone up to 4.5. We plot this function here. We see it crosses the x-axis at this point, about 2.6, somewhere below 2.9 and 2.5. We see that it crosses there, and that's the value that we're trying to solve with this function. And that's the normal depth. So let's go about doing this in an iterative way. So we need to put in the formulas into this table, but we also need to remember that some of them need to be set as constants when we drag the numbers down. So let's just go and do that and be careful about these constants. So the area is b times y, so b, which is a constant. And in Excel, to make something a constant, you put dollars, dollar, dollar. In Excel on a PC, you press F4 and it puts them in for you. If you press it again by accident, it takes one of them out. Press it again, it takes the other and swaps it. Press it again, it removes them all. Press it again, it goes back to the $2. That's what we want. So B times the guessed value of Y. I've always chosen a guess. I always start with a guess value of 1, just because it's helps us estimate whether we've got the formulas right, but it's also not a bad start. So P is equal to B as a constant plus 2 times Y. R is always equal to A over P. Q, we're just going to write this formula in. Q is equal to A times C as a constant times R. Now, Excel's not letting me put R in there, so I'm going to type it by hand, and that's R is E15. E15, I don't need the capital. All raised to the 0.5 times by S0 as a constant, raised to the 0.5 as well. So we see that's with that estimate of 1, we've got a Q of 8.2 meters cubed per second, and my target is 30. So we know that we're way off, but let's not worry for now. I'm going to skip the percent error, but for now, I'm going to the absolute error, or the value of the function, which will be Q as a constant minus the Q from the estimated value of Y. So we see that's 21 meters cubed per second out. That's just now we can use that value, that estimated function divided by Q. Let's just set Q as a constant there, times it by 100, and that gives us a percent error. It's 72% out, way out. Now we can drag this table, these numbers, this row, all the way to the bottom. We've got these formulas. Let's just check that I've got these right. I've put 1 in there, it should be exactly the same number. Okay, but 1's not a good guess. Let's try 2 meters. So we see that the absolute value error has gone down to 9, so that's good. Let's try 3 meters. Right, it's gone to -4. So we know that the solution is between that positive and negative, between 2 and 3. A little bit nearer 3, I think. So let's try 2.6. Okay, that's really good. We've now got we're in error of 0.89 meters cubed per second. Let's try 2.65. Okay, that's even better. 2.66. Okay, that's really good. So we're less than 1% out, less than half of 1% out. So 29.96 when we wanted 30. We'll leave it at that in terms of the trial and error. Let's go and have a look at how we do this with the secant method. Well, we've got this same table. We're going to copy that first row because it's exactly the same, and I can drag that down to the second row. Just check my numbers are right. 2, give me 9.2, 2, 9.2. Good. We need to, in this cell, guess a new value. With the secant method, that's what the secant method does. It guesses us that new value. And this is the formula we're going to implement in there. And it's a relatively simple formula. We start off with the last guessed value, and we subtract the function from the last guessed value. We times it by, well, we solve this bracket term, so we need a bracket. We actually need a second bracket, one for the numerator, one for the denominator. So the last guessed value minus the second last guessed value, bracketed, divided by the last function value minus the second last function value, and 2 brackets to close. So 2.733 is the next guessed value, which looks about right. So we drag that down, we see that the error is minus 1. So we know that there's a solution between those, between 2 and 2.7. We know that from above, but the good thing about this, now we can just drag that all to the bottom. And we see that very rapidly it's converged to 2.663 meters with an error of, well, less than 1 litre, less than 0.5 litre per second. Okay, so we've solved the normal depth given uniform flow. We've done 2 iterative solutions. Now we can use these tables again. We can use these tables again to solve all the questions. We just change the numbers. You've got a robust way of solving your normal depth equation in Chesney. Now we want to be able to do this with Manning's, because Manning's is much more common. So let's look at the Manning's example. Well, we've got the same shaped channel, the same rectangular channel. We've got a flow. We've been given a flow of 30 here, and we've been given a Manning's N of 0.02, although I just noticed that there's a mistake. That should say Manning's N, what the Manning's N is. Anyway, the Manning's N is 0.02. So we can sneakily just copy the formula from the row before. In fact, that would be a mistake, because remember that the Q is going to be calculated now with the Manning's N. So I'm going to type them all in again so we get that right. So A is equal to B constant times Y. B is equal to B, the constant is equal to B as a constant plus 2 times Y. R is equal to A over B. Q is now this formula. You can write it in various different ways, but I'm going to do the 1 over N to start with. N is constant there. Times it by R, which is this value raised to the 2/3. Now I could have put in 0.6667, whatever, in there, but I've put it in 2/3 in this format. And then it's S naught, and I've forgotten to type in S naught, so I'll type in S naught in a second. S naught fixed raised to 0.5, and that probably gives us 0. So I'm going to put in here the 1 divided by 1000. There we go. The absolute error is the Q constant minus Q. That error, we're trying to get a Q of 30 here. So this looks about right. Let me just have a look at this formula. I think I may well have got this formula wrong here. Yes, I've forgotten to multiply by the area here. So let's have an area in here times by r to the 2/3. There we go. That's much better. So always check your formula against what you've got. Let's calculate Q percent error. So it's that value divided by the target constant times 100. So we're 73% out. Let's drag this down now to the bottom. I'll put 1 in here to get the same numbers. Perfect. We're going to put 2 in. It's getting closer. Put 3 in. 2. So we've now got a change in sign here. So we know it's between 2 and 3. It's 2.5. Let's try this time 2.55. Oh, that's excellent. So we've got less than 0.5% of error. So okay, good. We've got now 2.55 for this this problem where the Lanning's n is 0.02. Let's do the next secant method to solve this. We can sneakily copy that top row from above, the table above, drag it down. We see that these numbers are the same, so we check they're okay. We need to put the secant formula in, this secant formula in here, this cell here. And again, we can be a bit sneaky because it's exactly the same table. We can copy it from the table before, type it in. So that's the guess this time. We can drag that row down. We can now drag all of those rows to the bottom. And we see that very quickly it converges to 2.552. Pretty similar to the trial and error method above. Let's now look at briefly at this section table. I'm going to show you this table several times. It's a summary of the formula that we need. Now we've seen the rectangular, we're going to see the trapezoidal. Trapezoidal is most useful because it can also simulate the rectangular. If you put the s, this lowercase s here, as 0. Formula for a circle are all here. These are definitely a lot more complicated and easy to make mistakes in Excel. One of the big things you need to remember is that theta is in radians when you do an Excel. Later on in the course, we'll do an Excel example with a circle. Let's have a look at example with a trapezoidal channel. So we've got the bottom width 2, we've got the side slope 2.5. Now this is how I define the side slope. So it's 1 in the vertical and however many s in the horizontal. So 1 divided by s divided by 1 would be 2.5. So s is 2.5, and this is shown in the formula here. Again, I conveniently write out the formula in my Excel, so I know what formula I'm going to be typing in. Lanning's n is 0.025 this time, and the normal depth is 0.5. So we want to know what's the flow this trapezoidal channel would carry in uniform flow. So the area is this formula. I'm going to need some brackets here. V plus side slope S times the depth times the depth. Area is 1.625. P is the bottom width plus 2 times the depth times, and we'll use the square root formula, 1 plus side slope squared. Just do side slope times side slope. Yep. R, as always, is A over B, and Q is just this formula typed in, is equal to, and I'm going to type it differently this time, A times R raised to the 2/3 times the bed slope S raised to the 0.5 divided by N. Now, you can put extra brackets in here if you think it'll help you get the equation right, but you don't need them. So the flow for this channel is 1.014 meters cubed per second. You noticed how I've only got 3 decimal places here. If you get many more than that, it gets confusing. And in fact, let's just look at R, for example. That's in meters, and you don't really need any meter length in less than a millimeter. So we'll keep it 3 decimal places, and the flow, we're down to 14 liters per second at the end here. So that's sufficiently accurate, liter per second. No, we don't need fractions of liters normally. So this was calculating the flow given a normal depth, but it's more tricky to calculate the depth given a flow. So let's have a look at this example. So we're looking at trapezoidal section. And we've got the formula for the trapezoid, a key here. We've got the formula that we're going to try and solve the value of y for. So that formula equals 0. So we just apply this iterative method again, as we've done before. We're going to put in the formula for the for area in here, which is B as a constant plus S side slope as a constant times our guessed value of y. Now Excel's not letting me type click on that, so I know that it's cell B18 times by, well, it's B18 again, so 8.5. The wetted perimeter is that equal to the B as a constant plus 2 times our guessed value of y times the square root of 1 plus side slope as a constant squared, close bracket. R, as always, is equal to A divided by P. Q, now we'll just write this formula out again, equals A times R. Remember that it's to the 2/3 in the Manning's equation, times by the bed slope as a constant raised to 0.5, and then we need to divide all that by n as a constant. Okay, the absolute error is just value of Q that we're targeting as a constant subtracted from the, and we'll subtract from that the value of Q from our guess value of Y. So we want 9, we're 4.5 meters cubed out per second out. Let's just type in the percent error now, divide the absolute value by Q as a constant and times it by 100. 47% out. Let's pull that down. 1, just do a check. We'll put 1 in here. We want to see that we've got the same numbers we have. Okay. 2. So we see that the answer here is between 1 and 2 meters, because that's gone from positive to negative. I'm going to drag that to the bottom. I'll put in 1.5. So we see it's below 1.5 because it's between 1.5 and 1. 1.4. 1.44. Okay, that's about good enough. So it's less than 0.1% out. So I think that's a good accuracy. Let's do it with the secant method, or we can copy this first two, put them into here, we'll guess the 1 and 2. Those two numbers are the same, so our formulas are right. We can put in here our secant formula. I'm going to type it in again because our table is slightly different to previously, or even if it's not, it's good to put it in again. So the y before from the function of the y before times by double bracket here, the y before minus the y before that, divided by a function of the y before minus the function of the y before that. Double bracket to close, that's our next guessed value, which is about right, because it's getting towards this 1.4. So let's just select that whole row, drag it to the bottom, and we see that after 6 iterations, we've iterated onto 1.440 with an error less than 1,000%. So 1.44, same solution there. Okay, that's the most useful sheet we've done up to now, because the trapezoidal channel can approximate a rectangular channel by putting s equals 0. So is it if those side slopes moved up, we'll see that the secant method has said it's 1.77 meters deep, which you'd expect that to be with no side slope, and we'll put that side slope back. We can approximate a V-shaped channel if we put b equals 0. So if we do that, we'll see how the secant method quickly comes down to 2.8. The trial and error, you have to put in your own numbers though. Last example, instead of the uniform flow equation, we're going to look at the critical, calculating critical depth and calculate the Froude number. Now, critical depth is a depth when the Froude number is equal to 1. So here's the Froude number, here's the Froude number squared, and both are useful because when the Froude number equals to 1 is equal to 1, so is the Froude number squared. The formula we'll be looking at is looking at both the Froude number and the Froude number squared and equating that to 1. So the function we'll be looking at is the Froude number minus 1 rather than the target Q. The target now is 1. So let's type in our formula again. So A, now the question is about a rectangular channel, but I'm going to do a trapezoidal channel because it's more generic. I've got the equations here to remind me. So A is equal to brackets B, bed width as constant, plus the side slope as a constant. And you see that the side slope is 0 because we're approximating a rectangular channel in this case, times by y, and I have to type that in as B18 again, B18 times close bracket times B18, the guessed value. And that comes out as 8. The top width is B plus 2sy, so it's equal to B as a constant plus 2 times side slope as a constant times y, our guessed value. Now it's 8 here because remember it's a rectangular channel, so the bed width is the same as the is going to be always the same as the bed width. So the top width is always going to be the same as the bed width in this rectangular channel. Froude number. So what's the formula we're using for Froude number? We're going to use this equation here, this formula. So that's equal to Q as a constant divided by the area we've just guessed, and we can say divided by square root. And the first thing here is G, so we've got a gravitational constant, make that a constant, times by the area we just guessed, divided by the width. It's not letting me type in the width, so let me type it in as letter D18. Close that, that should be good. I'm just actually going to make that one more decimal, because when we get to the Froude number squared, it'll show the slight difference. Froude number squared, well, there's two ways of doing that. We can do the Froude number times the Froude number, or we can use a formula. And this is the formula we're going to use. We'll use the formula, so it checks our Froude number for us. So let's do that is equal to Q as a constant squared times by the width divided by A cubed divided by G as a constant. Excellent. 1.43 is the same. The error, and I'm using 1 minus the Froude number. I'm using the Froude number. I could use the Froude number squared. This value here would be different, but when it comes to the solution, it would be exactly the same, because the Froude number squared will be 1, the Froude number will be 1. Let's pull that down. Let's check. I've put 1 in here, we've got the same numbers. Yes, we have. We're going to guess 2. Well, we can see that the answer is between 1 and 2, and a little bit nearer 1. So let's do what? But let's do 1.5. Not let's drag the whole lot to the bottom. So 0.3. So 1.125. I'm going to go for. I should be 1.25 as a formula, and it's still less than that. So 1.125, and that's pretty good. We're looking for 1 here, and it's nearly 1. And only a slight error. Let's look at the secant method, or we can copy those first 2 rows if we've done them right. Yes, they're giving the right values. The secant method here, well, we did a trapezoidal section last time. Can we use that? The secant method, we probably could, but we're not sure. So let's type it in again. Remember, the secant method formulas here, always have your formulas handy. So it's the last value minus the function from the last value times the last value minus the second last value divided by the function of the last value minus the function of the second last value, 2 brackets to close, and we're getting 1.255 from the secant value. Let's smooth that all along to the bottom, and we see this converges to 1 for the Froude number scales 1.127. So we'll just type that 1.127 in there, 1.127 in there, and we get almost the same. So we'll probably find that this is slightly 1.1275. If we put that in there, we'll see, yeah, we're getting the same. Now I've typed it in that second last value because the question asks if uniform flow is 3 meters, flow depth or normal depth is 3 meters, what's the Froude number? So we've got a 3 here. I can put in 3 here. Just going to call it that so show that it's slightly different. And the Froude number is asking for it is giving us is 0.23. So 0.23 is less than 1, so it's subcritical flow. So the answer there is that it's subcritical flow. And we know that also because we've got a 3 here and we've got a 1.2. So that's deeper than 1.2, the critical depth. Okay, we'll see more about critical depth and normal depth comparisons later. Okay, I'm going to finish there. Thank you.